Hey everybody, this is 11F. Will the string break? It says a teacher wishes to set up a demonstration that involves connecting a bowling ball of mass M to a fixed point O on the ceiling by a string. The distance between O and the center of the ball is L. The teacher plans to exert a horizontal force to pull the bowling ball to position P right here, where the string makes an angle of 60 degrees to the vertical, holding the ball in place at time T1. The teacher then plans to release the ball from rest so that the ball swings down to point Q, where the string is in a vertical line at T2. However, the teacher is concerned that the tension will be too great at point Q, and the string will break at time T2, and the bowling ball will become a projectile. So that is the setup for this situation. So next part, it says part A. Let me grab this here. Oop, hold on, my pages are sticking together. All right. So part A, the dot below represents the bowling ball at the locations and moments mentioned. Draw a free body diagram showing and labeling forces, not components, exerted on the ball, each ball. Draw relative lengths of all vectors to reflect relative magnitudes of all forces. So this is the ball is at rest at point P. So again, that is right here when we're holding it there. So we can clearly see we're going to have tension because of the string and gravity because of we're on Earth, and the teacher is pulling the ball back this way here. So, and it says the teacher exerts a horizontal force on it. So let me draw some forces here. So 1, 2, 3. I'm going to draw this one to the side, and I'm going to call this FA. This is the applied force from the teacher. No reason to draw it 3 blocks long. It's just an arbitrary choice. We know that we will have gravity acting on it. I am going to draw that 2 blocks down. So that is the force of gravity there. And then also, we are going to have tension. Now, how do I angle this tension? Now, be careful here. Don't draw the components. They said that. But I know that this one has to balance out these other 2. So that means we must go 1, 2, 3 to the side and 1, 2 up, just like this to match these 2 here. So right there, this must be the tension. Now, I'm going to do something they just told you not to do, but just to illustrate this point here, that we must have on this side here to balance out this horizontal applied force, we must have a tension in the X that's equal to that, so it doesn't move horizontally. And then also, so that it doesn't move vertically, we must have a tension in the Y that balances out that force of gravity. But again, if you were drawing this on the actual answer, don't draw those 2 because they told you not to do it there. All right, so next part right here is, where did I put it? Here it is. So it says the ball has been released and is at this instant is passing through point Q. So it is now down at the bottom of the page here, so it's right down here. So now, at point Q, it is going to have gravity acting down on it. By the way, gravity won't increase just because it's at point Q, so I'm going to still draw it 2 long there. And we will also have the string pulling on it, and I'm going to draw that 1, 2, 3, 4. So tension is still pulling up. Now, how do we know tension's got to be bigger than gravity? Well, because at the bottom of this circle, it is going in a circle, and so it must have a centripetal force on it, which means the force is towards the center, that is the tension, must be bigger than the force of gravity trying to pull it out of the center. In a little bit, we'll see why I know, looking ahead, I've already done that tension must be twice as big as gravity, but we'll get to that in just a second here. All right, next up, part B. It says, using conservation of energy, use conservation of energy to derive an expression for the speed of the ball at point Q in terms of G and L. All right, so we know that we have gravitational potential energy becoming kinetic energy. We know that generically gravitational potential energy is mass times gravity times height, and kinetic energy is 1/2 mv squared. That's what we're looking for. Masses on each side cancel. So now let's just plug in for our height. That h there is generic. They tell us here that our height, we can see it right here, we are 0.5 times the length of the string up. So that is our height right there. So I'm going to plug in for h, I'm going to plug in 0.5 L. That is equal to 1/2 times v squared. By the way, this 0.5 cancels with that half there. And so now we just need to solve for v. V will equal the square root of g times L, since v squared equals GL there. Okay, now next part. Part C says, to determine the tension in the rope at the 2 moments indicated, so time 1. So time 1 is when we were holding it in this position right here. So what is the tension? And to sort of get that, let me come back to this picture right here. So I know from this picture right here, I know that Ty is equal to Fg, as I've already mentioned. So that is the same as mg. And then I know that this angle is 60 degrees. Let me draw that a bit bigger again on here. So I know that I have a vertical component that is Ty that is equal to mg. And over here I have T. And we know that this angle here is 60 degrees. So I can use some trig to figure out what T must be. According to geometry, the cosine of an angle is the adjacent side over the hypotenuse. Well, in this particular case, our angle is 60 degrees. Our adjacent side is mg, and our hypotenuse is the tension that we're looking for. So I'm going to multiply the t up here, bring the cosine 60 down there. So t is equal to mg over cosine of 60 degrees. And cosine of 60, if you don't know, that's fine. You can plug it in your calculator. It's a half. So mg divided by a half is 2 mg. So the tension at that first point, time t1, is 2 mg. Now let's find it here at time t2. This is going to be a centripetal problem. And so if we go back to our free body diagram that we made here, remember the center's up here. We know that the overall, these two forces together are causing us to go in a circle, so we can write this, that the tension minus mg, the weight, that those two together, the sum of those makes us go in a circle. So those must be equal to mv squared over r, the mass times the centripetal acceleration. So let me add the mg to the other side. So the tension will be mass times gravity plus mass times velocity squared over the radius. So we're almost there. Let's add in some substitutions here. So mg plus m. Now we just solved for that velocity. That velocity that we just solved for is right here. It's the square root of GL. So if we square the square root goes away and it's just GL. Now, what's the radius? Well, the radius that we are swinging on is the length of the string itself. So L by the time we get down here. So the radius is also L. So the L cancels the L and we wind up with mg plus mg. So the tension here is also 2 mg. So now last question here. It says, if the string does not break at time t1, then does the teacher need to worry about letting go of the ball? Then the teacher does not need to worry about letting go of the ball. Explain why using your answers to part C. Well, the tension in part 1 is the same as the tension in part 2. So if it doesn't break there, it will not break there.